Assalamu alaikum. Please get settled down. Please get settled down. वालेकुम सलाम. देखिए वहाँ से हैं. All right. So yesterday we looked at the particle in a well problem, and there are important lessons for us to learn from this problem. So our potential well is such that to the left of x equals 0, for negative x values the potential energy is infinity, and to the right of this wall the potential energy is infinity. I think there is someone standing in front of you trying to say something. And we solved the Schrödinger equation for this problem, and we noticed first of all that energy is quantized, En. So there is an index n that appears, and this energy is given by n squared pi squared h bar squared over 2m L squared, where m is the mass of the particle and L is the length of this wall. So what we could say is that there are in fact discrete energy levels for the electron inside this well. And as n goes up, so this is n equals 1, which represents the ground state, n equals 2, the first excited state, n equals 3, n equals 4, and so on. And the spacing between these levels is not constant. It increases quadratically. So En is proportional to n squared. If L goes up or goes down, the spacing changes. And we looked at a demonstration yesterday to the same effect. So energy has become quantized, and we have found out what the energy levels are. So in the course before the midterm, you were constantly asking me questions, how do we get these energy levels? So now we've seen one real example of what those energy levels really are and what they look. So what we need is the potential energy function, we put it into the Schrödinger equation, and the energy levels pop out. So now here the electron is confined within this well. It cannot go outside the well. It's doomed to exist inside the well. Hence, its energy becomes quantized. Whenever you have a system and you restrict its realm of positions, if you restrict the area or the volume that it can visit, its energy becomes quantized. So confinement leads to quantization. So this is something that we observed yesterday. One thing you readily notice is that when the system is in the ground state, when it has the minimum energy, that minimum energy is not really zero. There is some minimum energy, E naught or E1 here in this notation, E1. The minimum energy when n equals 1, and that is given by pi squared h bar squared 2m L squared. So this is the minimum energy the electron will have in its ground state. So if you take this system and put it inside a bath that is at 0 kelvins, you put it at 0 kelvins, absolute zero, there will still be some energy for the electron, and that energy is not going to be zero. So this minimum energy is called the 0 point energy. Hence, another important lesson is that in quantum mechanics, the energy of an object can never be zero. There is always some minute energy for the system, even if you cool the system at 0 kelvins. इधर तवज्जो करें कि alright, question. If you're at 0 kelvins, which energy level is populated? The ground state. So if you have one electron in a potential well, it will be here. If you have another electron, so if I draw many potential wells, say if I have 4 electrons, and each one of them is in a potential well, and there are quantized energy levels, and so on. So at 0 kelvins, all 4 electrons will be in their ground state levels. If I raise the temperature, there is a probability that each one of these electrons can be excited to a higher level. So if I have 4 electrons in 4 different potential wells, but identical potential wells, I can also represent this schematically, conceptually, by putting all the 4 electrons here. Okay, so this picture is a schematic equivalent of this picture. It may not necessarily mean that you have one potential well and all 4 electrons are in the same potential well and all 4 of them are in the ground state, because there are restrictions imposed by Pauli's exclusion principle. We'll deal with that later. But this is a schematic representation of this scenario. Now if you raise the temperature, an electron can jump to a higher state, to an even higher state. Okay, so it can make upward transitions. And when this electron goes to a higher state, it can come down, make downward transitions, and emit our ubiquitous photons. Okay, so it can absorb a photon and be excited to a higher energy level, or it can be placed at some temperature. So excitation takes place, and then since the electron cannot stay in the excited state for long, every excited state has a lifetime, the electron has to come down and it will emit photons of precise frequencies, certain frequencies. Alright, so there is some 0 point energy, say there is some residual energy, some energy even in vacuum. Alright, so this is one important point that I wanted you to keep in your minds. The other important point is about the wave function itself. If the electron is in the ground state, and I ask you the question, where is the electron? First of all, this question is bogus, as I've told you already. You cannot ask this question and expect a reasonable intuitive answer, because the electron is everywhere inside this well before you measure it. And when you measure it, the wave function or the field collapses, and you find the electron to be at a certain point with a certain probability. Okay? If the electron is in the n equals 3 state, the second excited state, and you ask where is the electron, you cannot say for sure where the electron is. Okay? So what you can say is that the electron is everywhere. It's smeared out in this region. It's a field that's everywhere, and when you want to look at the electron, this field will collapse at a certain value of x. So let's plot the wave functions now. Alright, one thing, these energy levels, they come out from Schrödinger equation. So we have a potential well, we've calculated the energy levels. and they have an n square dependence. The energy has an n square dependence. For the hydrogen atom, and these energies are positive. For the hydrogen atom, we found out the energy levels to be minus 13.6 over 1 electron volts, minus 13.6 over 4 electron volts, minus 13.6 over 9 electron volts, and so on. And the energy levels get closer and closer together. And this is E equals 0. So these are the energy levels for the hydrogen atom, as we've already seen time and time again. So these energy levels come from the Bohr's model, but they can also be derived from the Schrödinger equation. Okay? Fortuitously or by luck, by a happy accident, both of these energy level calculations give you the same results. The Schrödinger equation and the old quantum theory gives you the same results for the energy. Where the old quantum theory fails or breaks down is it is not able to define the position of the electron. Okay? So these energy levels in the hydrogen atom also come out from the Schrödinger equation, provided you use the correct potential energy function, VR, which for the hydrogen atom is 1 over 4 pi epsilon naught R. So use the correct potential energy function, these energy levels will pop out by themselves. So it is the Schrödinger equation that tells you what those energy levels are. If you have a harmonic oscillator, then the energy levels are equally spaced. Okay, so you have some energy E1, this is E2, this is E3, and we already know that the energy level spacing is constant. It's some h bar omega, and these levels are constantly spaced in a harmonic oscillator because the harmonic oscillator has a special kind of potential energy function. So the potential energy function for a harmonic oscillator is half, as you all know, kx squared. And it looks like this. So if you use this potential energy function and put it into the Schrödinger equation, you will get equally spaced levels. If you use the infinite potential well, you will get these levels. If you use the potential energy function for the hydrogen atom, you will get energy levels that are spaced by this. So it is the one equation, the Schrödinger equation, that tells you how to find out those energy levels. And the energy levels tend to be quantized whenever you confine the system. If the electron has energy which is positive in the hydrogen atom, the electron is no longer confined to the system, and its energy then becomes not quantized but continuous. So any electron that is not bound to the nucleus in a hydrogen atom, when it's not bound, its energy is not quantized. Its energy is really continuous. Okay? So you've been asking me questions again and again about how do we get these energy levels? How do we know that the energy levels in an harmonic oscillator are equally spaced? In an infinite well, they increase quadratically. In here, they decrease, the spacing decreases quadratically. How do we know this? It comes out because of the Schrödinger equation. Now let's plot the wave functions for the infinite well again. And a lot of beautiful unified quantum mechanics can be learned from looking at the infinite well. Alright, so we have these energy levels. Okay, one question. If I'm at temperature T and I have this energy E2 and this energy E1, and this system is placed at temperature capital T, I want to find out the ratio of the populations of levels E1 and E2. How do I do that? Can you please write down that ratio for me?
So the ratio of population to energy level.
E2 and E1. This is proportional to, okay, right, so this is the ratio, okay, good, that's the ratio. समझ नहीं आई? देखो पुरानी चीज़ों को भूलना नहीं, ये नहीं आपने कहना कि मिड टर्म से पहले जो पढ़ा है मैंने वो मैं हज़्फ कर दूं अपनी याददाश्त में से और आगे मेरे काम नहीं आएगी वो चीज़. You cannot fragment any course into pre-midterm and post-midterm, into freshman, first semester, second semester. No, everything is a continuous organic whole. N2 is the upper, right? It's fine. जी क्यों क्यों किया किधर जा रहा? नहीं अभी तो क्लास होगी. शाबाश, that's fine, that's fine, that is fine. So I think most students have been able to identify what the result is. If there are N2 electrons in E2 and N1 electrons in E1, the ratio N2 over N1 is going to be exponent minus the upper energy level E2 minus E1 over KBT. It's just the Boltzmann distribution. Alright, now the wave functions. Outside the well, the wave function is 0. It disappears. Now I would like to draw a clean diagram once again, an uncluttered diagram, because I want to show several things to you all in one go. We know that the wave function inside the well is given by 2 iota a sine of n pi x over L. Now this number n is called a quantum number. It's a quantum number. And how many dimensions is our system in? How many dimensions do we have here? Just one dimension, just along x. So there is only one quantum number. Okay? Baat suno. There is only one quantum number. For the hydrogen atom, if you have orbitals, for example the s orbital, the p orbital, the px orbital, and so on, how many dimensions does the hydrogen atom exist in? It's a 3-dimensional object. So there must be 3 quantum numbers. For a 2-dimensional object, if this is a sheet and the electron is confined to move in this 2-dimensional sheet, there will be 2 quantum numbers for it. In 3 dimensions there will be 3 quantum numbers. So for the hydrogen atom and an electron inside a hydrogen atom, there are 3 quantum numbers. And the wave functions are called orbitals. So Schrödinger mechanics tells you that there are no orbits but orbitals. And those 3 quantum numbers are labeled n, L and ml. Okay? So you solve the Schrödinger equation for the hydrogen atom in 3 dimensions, you'll get 3 quantum numbers. N quantizes the energy, L quantizes something else, ml quantizes something else. Okay? So every quantum number quantizes some property. Here n is quantizing the energy. Okay? Now if we have this wave function, first of all what I would like you to tell me is it possible to find out the value of A? Is A just arbitrary? Suppose I can put a small n here with the wave function because there is an n here. Suppose for simplicity I take n equals 1. So psi 1 equals 2 iota a sine of pi x over L. Okay, so this is in the wave function in the ground state. Okay, it appears to be a complex number. Okay, I want to find out the value of a. How can I find out the value of a, and is it possible at all to find out what a is?
By using probability and equaling it to 1.
समझ आई?
By using the normalization condition.
Right. So what is a wave function? Wave function की क्या physical significance है?
If we take the square of it and then
Modulus squared of it. What do we get?
integrate it, we get the probability of it, and if we sum it to 1.
Right. So this electron must exist somewhere in space. Otherwise we're talking about a fictitious ghost. But the electron is not a fictitious ghost, it's a real particle. So it must exist somewhere. But it can't exist outside the well. So it must be trapped somewhere inside the well. So the probability of finding this electron inside the well is 1. You're bound to observe the electron inside the well. Hence, if I take this integral, I take the modulus squared of this and integrate this between the limits 0 and L. I should get 1. So I take the modulus squared, the 2 का square is 4. Iota का modulus squared क्या है? -1. 1. Iota का square -1 है, लेकिन modulus squared is iota conjugate iota, which is minus iota into iota, which is +1. So इसका modulus squared is 1. I get a square here. I get sine square pi x over L dx equals 1. Can you please find out what value of a should I get? हमने याद है वेव फंक्शन की फिजिकल रिक्वायरमेंट्स. एक फिजिकल रिक्वायरमेंट ये है कि this means the probability density, so the probability must be 1 of finding it somewhere. Can you please find out a? जो बड़े डॉक्टर साहब आते हैं ना, छोटे डॉक्टर पहले वो मरीज को तैयार कर देते हैं सारे एनेस्थीसिया वगैरह देके. बड़े डॉक्टर साहब आते हैं वो सिर्फ ऑपरेशन, मेजर ऑपरेशन करते हैं और फिर चले जाते हैं. तो हम सारी आपकी तैयारी कर रहे हैं कि आप क्विज देंगे.
तो क्विज के लिए नहीं
पढ़ने नहीं आए थे.
लेक्चर पूरा हुआ नहीं हुआ. आई एम सॉरी.
One is cosine from 0 to L. Maybe. Yeah.
So isn't it a certified identity that when it's like it's also linked with that?
Yeah. So you can perform this calculation on your own, and you put in the final value of a that comes out from this integral. Your wave function psi n comes out as 2 over L under root sine of n pi x over L. So this is your final wave function, n pi x over L. Now let's plot this wave function. For n equals 1, देखो अब जरा ध्यान से बात सुने, it's very important. If n equals 1, you're in the ground state. So what is the wave function? For the wave function, you put n equals 1, you get sine pi x over L. At x equals 0, this is 0. At x equals L, this is pi. So sine of pi is 0 again. So you have a wave function that is 0 at the walls and looks like a sine function. And the wave function is 0 outside the well, as it should be. So this is the wave function of the electron in the ground state. If the electron were in the ground state and it possessed energy E1, then its wave function is going to look like this. Okay? Now what about the first excited state? For the first excited state, I put n equals 2. So if I put in a 2 here, this becomes sine 2 pi x over L. And you can find out where this function goes to 0. It goes to 0 here. It goes to 0 in the middle. It goes to 0 here. So I will plot a sine function like this. This is the wave function of the electron in the first excited state. Then I take the next level. N equals 3 here. I put sine 3 pi x over L. And the wave function that I plot looks like this. This wave function has 3 nodes. 1, 2, 3. A node is a point where the wave function is 0. This wave function has 2 nodes. This wave function will have 4 nodes. So if you are in the nth state, there will be n plus 1 nodes. So this is the wave function. How the wave function of the electron looks like. And if you were to talk about the probability distribution of the electron, I can draw another diagram for the probability density. If I take the modulus squared of this wave function, I will get the probability density. So this function is the modulus squared of this function. For this function is telling me that the electron is avoiding the walls. There's very little probability of finding the electron near the edges of the potential well. And there's very high probability of finding the electron in the exact center. If the electron is in the first excited state, I take the modulus squared of this wave function. This is what I obtain. So if the electron is in the first excited state, you will never find the electron in the exact center of the potential well. This is a forbidden point for the electron. So you measure where the electron is in an experiment, it will never be found at the center of the well. So how does an electron get across from the left side of the well to the right hand side? Again, this is a bogus question to ask, because the electron cannot be viewed as a particle in motion. It's a wave function that is spread out in space. And if I keep on increasing the value of n, so for low n's, my probability density function looks like this. Then for higher n, this. If I keep on increasing the value of n, I get more and more nodes inside the well. So for very high n, the wave function squeezes. In other words, the wave number decreases, the value of k goes up, and the potential distribution function starts looking like this. The wavelength becomes so small, or the value of k becomes so high, that you start observing classical effects, that the quantum effects break down. Because now your wavelength is so small that it is imperceptibly small, and in your real life you cannot observe what the wavelength really is. So for large values of n, the quantum effects start becoming hazy. They start fizzling out. This is called the correspondence principle. We'll have more to say about this in our lecture on Tuesday. But for a change of taste, let's have a quiz now.